Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the sixth numerical on spread spectrum modulation. Please note this is a numerical on fast frequency hopping. Specifically, it is on fast frequency hopped MFSK system. Let me read out the question first. A PN sequence is generated using a 4-stage linear feedback shift register shown below with the initial condition 1 0 0 0. This sequence is used in a fast frequency hopped MFSK system. The FH-MFSK signal has the following parameters. Parameter 1, number of bits per MFSK symbol capital K is equal to 2. Parameter 2, number of MFSK tones capital M is equal to 2 power capital K, which is equal to 2 power 2 and is therefore 4. Parameter 3, length of the PN segment per frequency hop, which is small k, is equal to 3. And lastly, parameter 4, total number of frequency hops, which is 2 to the power small k, is equal to 2 power 3 and is therefore 8. Coming to the linear feedback shift register, it is a 4-stage shift register with the initial condition 1 0 0. Here, each of the flip-flop is named as C3, C2, C1 and C0. Further, since it is a feedback shift register, a combination of C1 and C0 are added to a modulo 2 adder and is fed back as input to the shift register. Also, the contents of the flip-flop 4, which is C0, creates the output sequence. Let us now look into what is being asked in this numerical. Part A of the question says, determine the period of the PN sequence. Part B, determine the PN sequence for one periodic length. Part C of the question says, illustrate the variation of the frequency of FH-MFSK signal for one complete period of the PN sequence. Assume that the carrier hops to a new frequency twice every MFSK symbol or after transmitting one information bit. Assume binary data sequence to be 0110, 1100. Lastly, part D of the question says, sketch the variation of d-hopped frequency with respect to time. Right. With that, let us now start with the solution part. Please note, we are given a fast frequency hop MFSK system. We should note that in a fast frequency hopping system, the rate of change of carrier frequency, which is nothing but the hopping rate, is greater than the rate of change of the input symbol, which is symbol rate RS. Here, for this particular numerical, we are told the carrier changes to a new frequency every single digit. So, the chip rate RC is equal to RH. Therefore, now I can say that in a fast frequency hopped MFSK system, carrier hops to a new frequency after transmitting every information bit. Another very important thing to note here is that in the parameters of the fast FH-MFSK system that is given, look at the third parameter here. The third parameter says the length of the PN segment per hop, which is small k, is equal to 3. So, we have to now understand that the carrier frequency changes to a new value or it hops to a new frequency value after transmitting 3-bit length of the PN segment or after transmitting every information bit. Right. Let us now start with part A of the question. Part A of the question is to find the length or period of the PN sequence. To find the length or period of the PN sequence, we need to look at the number of flip-flops in the linear feedback shift register. Here we are given a 4-stage shift register, which simply means there are 4 flip-flops in the shift register. So, I will write that down here. It is represented by m and is equal to 4, which means there are 4 flip-flops. After finding the number of flip-flops, the equation for the length or period of the P-n sequence is quite straightforward. It is simply equal to 2 to the power m minus 1. I will write that one here. It is generally represented by capital L and, as I said, is equal to 2 power m minus 1. Here m is equal to 4 and therefore the length or period of the P-n sequence is 15 bits. That is the answer for part A of the numerical. Let us now move on to part B, that is to find the P-n sequence for one period length. To illustrate the P-n sequence generation, I am going to construct a small table here, and the table looks like this. Right. Here in this table, the first column, that is the leftmost column, is dedicated for clock. Please note the length of the P-n sequence or the period of the P-n sequence is 15. So, if I start the clock pulse from 0, the length of the P-n sequence will continue till 14. So, I will now write the clock pulses from 0 to 14. Coming to the second column, these represent the content of the linear feedback shift register. Please note, in the numerical we are given the initial condition of the linear feedback shift register is 1000. To create the P-n sequence, we now compute the feedback term, and the output bit across each clock pulse is equal to the value of the last flip-flop, which is C0. So, coming to the feedback term, it is a modulo 2 addition of C1 plus C0. Let us start the operation. Compute the feedback term, that is 0 plus 0, this is equal to 0. The output bit, which is in the last column, is equal to C0. C0 here is 0, so just write 0 here. In the next clock pulse, the feedback C3 has to be replaced into the content C3 here. So, this 0 is placed here, that is the feedback C3 0 is placed under this C3. This one is shifted here, this 0 is shifted here, this 0 is shifted here. Now, repeat the operation, that is compute the feedback, which is C1 modulo 2 addition with C0, which is 0 plus 0, therefore, it is still 0. The output bit is C0, C0 is still 0, so this is also 0. Now, simply repeat the operation. So, the feedback C3 comes to this C3 here, this is moved here, this is moved here, this is moved here. So, the feedback term now is 1 plus 0 modulo 2 addition is equal to 1. Output bit is C0 and is therefore still 0. In this fashion, continue the computation of the C3 as well as the output bit till clock number 14. Right. So, we have now computed the P-n sequence till clock number 14. Let me now show what happens at clock number 15. If you compute the same for clock number 15, you will find C3 coming here. So, it would be 0, 0, 0. If you look at the feedback shift register content now, it is equal to 1000, which is what we started the overall operation. So, we now say that once the P-n sequence is generated for the given length or period, the next steps in the generation of the P-n sequence is simply going to repeat the overall operation. So, we will now say it is repeated. The P-n sequence is stored in the contents of the last column, which is the output bit C0 column. Please note, it is always from top to bottom. So, the P-n sequence generated is given by, it is 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. This is the P-n sequence. If you compute the number of bits, you will find it is equal to 15 bits, which is what exactly is the computation that we obtain at the part A of the numerical. Right. That completes part B of the question as well. Let us now move on to part C. I'll reread the part C of the question. It says, illustrate the variation of the frequency of FH-MFSK signal for one complete period of the PN sequence. Assume that the carrier hops to a new frequency twice every MFSK symbol or after transmitting one information bit. Assume the binary data sequence to be 0110, 1100. Before I start answering for this part of the numerical, I want you to note down there are 4 MFSK tones. I'll start my answer with that. Also, if you go back to the numerical and see the last parameter, which is this one, we are told there are totally 8 frequency hops. We will note that as well. So, what I will now do is create 2 tables, one for the frequency hop frequencies, the second one for the MFSK tones. Let me first start with the carrier hop frequencies. Right, this is the table I will be using. The first column says PN sequence segment. The second column is for the hopping carrier frequency in terms of hertz. If you come back and look at the numerical, particularly the parameter 3 of the FH-MFSK, you will note that the length of the PN sequence per hop, which is small k, is given as 3. So, now in the left column or the first column of this table, I have to write the PN sequence segment as a combination of 3 bits. The only possible answers for this would be starting from 000 and continuing till 111, which I will do it here. Further, every PN segment here represents a hopping carrier frequency. For example, for 000, let the hopping carrier frequency be denoted as FC0. For 001, let it be FC1. For 010, it is FC2. Continue in this fashion. This table now represents the PN sequence segment and the corresponding hopping carrier frequency in terms of hertz. Moving on, I will create another table, but this time for MFSK tones. We are told there are 4 MFSK tones which simply represent the 4 input signals. Therefore, I will now represent each signal with a separate MFSK frequency. Let me write that table here. Okay, this is the table. The left column represents the bits of the MFSK symbol and the right column represents the MFSK tone in terms of hertz. Note that we are told there are 4 MFSK tones. Each tone here represents an MFSK symbol of duration 2 bits. So, here I will write a simple 2-bit combination table starting with 00, 01, 10 and 11. And for each of these MFSK symbols, I will represent a frequency. For example, for 00, I will assign a frequency given by F0. 01, let it be represented by F1, 10 is F2 and 11 is F3. These are the frequencies for each of the input MFSK tones. With that information, now we are ready to move on to plot the transmitted frequency as a function of time for the given binary data as well as the generated PN sequence at the part B of the question. I'll start with the x-axis, which represents the time axis. Y-axis represents the bandwidth and is in terms of frequency. Starting with the x-axis, please note we are given a binary sequence of length 8 bits. So, I will now divide the x-axis into 8 intervals. Please remember these are bit intervals, not symbol intervals. Right, let me start by first writing down the input binary data just below the x-axis. Please note every interval here represents 1 bit only. The first input bit is 0, then we have a 1, then we have 1 again, then it is 0. The next 2 bits are 1 1 and the last 2 bits are 0 0. This is our input binary data. Below this, I will write the PN sequence. Now, it is very important to note that the carrier frequency changes to a new value or simply it hops to a new value after transmitting every bit of the input binary data or after transmitting a segment of the PN sequence of length 3. So, here I have to now associate one PN segment of length 3 with each of the input binary data. Remember, we are supposed to take the PN segment as what is generated in the part B of the question. If you go back and check the part B of the question solution, you will find the first 3 bits of the PN sequence are 0 0 0. So, I will write that under this interval. The next 3 bits of the PN segment are 1 0 0. They will be written here. The next 3 bits are 1 1 0. They will come under this bit interval. The next 3 bits are 1 0 1, which are under this bit interval. And lastly, the last 3 bits are 1 1 1, which are written here. However, we note that we still have 3 bits of information data to be transmitted. So, in such a case, simply repeat the PN sequence from the beginning. So, the first PN sequence segment, which is 0 0 0, will appear here as well. The next one appears here and the next one appears here. After this, let me concentrate on the y-axis. We are told there are 8 carrier hopping frequencies. So, I will divide the y-axis into 8 intervals, each interval representing a carrier frequency. The origin itself is represented by FC0, which is our very first carrier frequency. Here somewhere is FC1, then we have FC2, FC3 and continue in this fashion. After this, we have to now divide each carrier frequency interval into 4 more parts because we have 4 MFSK tones. The location of FC0 is also equal to F0, which is our very first MFSK tone. Let this be F1, this be F2 and let this be F3. So, every carrier frequency interval is further subdivided into 4 frequency bands representing each of the MFSK tones. After this, we move on to the next step, which is to identify the frequencies assigned to each of the PN segment as well as the input binary data. Let me start with the PN segment first. The first PN segment here is 0 0 0. Go back to the table here, identify where is 0 0 0 and find what is the associated hopping carrier frequency. For 0 0 0, it is FC0. Come back to the table and write here FC0. So, this will also be FC0. The next PN sequence segment is 1 0 0. Go back to the table, 1 0 0 represents FC4. Come back and write FC4 here. Next one is 1 1 0. 1 1 0 represents FC6. I will write FC6 here. Then we have 1 0 1. 1 0 1 stands for FC5. So, this is FC5. Lastly, 1 1 1, it stands for FC7. After 15 bits, the PN sequence simply repeats itself. So, the next 0 0 0 PN segment is nothing but the first 0 0 0 PN segment and therefore, it is FC0. Next one would be FC4 and the last one would be FC6. After identifying the hopping carrier frequencies, we will repeat the same, but now for the input binary data. However, please note the second table what we created is for 2 bits of information or simply one MFSK symbol at a time. Therefore, when we are considering the input binary data, we are supposed to consider 2 bits of information at a time. The first 2 bits across the input binary data are 0 and 1. Go back to the small table here. Find what is the associated MFSK tone for 0, 1. It is F1. Come back and write F1 here. So, F1 spans this complete symbol duration. Next, we have 1, 0. 1, 0 stands for F2. Then we have 1, 1. 1, 1 stands for F3. Lastly, we have 0, 0. 0, 0 stands for F0. After identifying the associated frequencies for both the PN sequence segments as well as the input MFSK tones, the next step is to plot the transmitted frequency itself. Please note, in slow as well as fast frequency hopping, whenever the carrier is transmitted, it is transmitted in terms of FCI plus FJ, where I stands for one of the hopping frequencies and J stands for one of the MFSK tones. If I follow this concept, apply the same to the first input digit, which is our 0. Please note, the PN sequence changes after every information bit. So, you have to now consider 1 bit of information for every box that is drawn on this particular graph. Start with the first bit 0. However, 0 is associated with the MFSK symbol 0, 1. So, we will consider F1. Coming to the PN sequence, we have FC0. So, the transmitted carrier frequency during the first bit interval is FC0 plus F1. We need to now write a box for this carrier frequency. Note that FC0 is just here, that is at the origin, and we have F1. F1 is this particular point. So, I will now write a small box for FC0 plus F1. I will write the same just above that box. Coming to the next bit is a 1. However, this is associated with the MFSK tone F1. So, F1 will be retained for the next bit interval as well. But what changes is the PN sequence segment. This bit interval has a PN sequence segment of 100, which is FC4. So, I have to now go for FC4 on the graph, which is here, and draw a box across the frequency FC4 plus F1. Moving on to the next bit interval, we have a 1, but this 1 is associated with the MFSK tone 10. 10 represents F2. Similarly, when we come to the PN sequence segment, we have 110. 110 represents FC6. So, for the third bit interval, the transmitted carrier frequency is FC6 plus F2. Note that FC6 is here and F2 is here. Moving on to the next bit is 0, but anyhow this is for the MFSK tone 10. So, F2 is retained, but PN sequence has now changed to FC5. So, the transmitted carrier frequency for this bit duration is FC5 plus F2. Note, FC5 is here, F2 is here. So, I will have to now write a box across this particular point. In a very similar fashion, you can extend this principle to plot the carrier frequencies for the rest of the MFSK tones. I am going to now very quickly illustrate the same for the rest of the input MFSK tones. The next 2 bits are 11, 11 represent F3. So, F3 is carried forward for the next 2 bit intervals. However, for the first bit interval here, we have the PN sequence segment equal to 111. 111 represents FC7. So, the transmitted carrier frequency for this one is FC7 plus F3. Let us go to this point. This is FC7, this is F3. So, I will have to now write a box at this point. Coming back, the next PN sequence segment is FC0. F3 is carried forward. So, for transmitting this bit 1, the transmitted carrier frequency is FC0 plus F3. FC0 is the x-axis itself, F3 is this point. So, I will have to now write a box here. Moving on to the next MFSK tone, we have 00. 00 represents frequency F0. The PN sequence for the first bit interval here is 100. 100 is nothing but FC4. So, the transmitted carrier frequency is FC4 plus F0. Lastly, the last PN sequence segment is 110, which is FC6. So, the transmitted carrier frequency for the last bit here is FC6 plus F0. Right. This is the plot of the transmitted frequency as a function of time for the given binary data and the generated PN sequence for the fast frequency hopped M-ARRY FSK system. Please note, in a fast frequency hopped system, the carrier frequency hops to a new value multiple times within one symbol duration. Particularly for the given numerical, the carrier frequency hops to a new value twice every symbol interval, or in other words, the carrier hops to a new frequency after transmitting every information bit. Right, that is the answer for the part C of the numerical. Lastly, I move on to the part D, which is to plot the D-hopped frequencies. We are asked to plot the D-hop frequency with respect to time. This is very simple. All you now need to do is borrow the transmitted carrier frequencies from the part C of the numerical and eliminate the carrier frequency parts from the transmitted frequencies. For example, if you look at the very first bit interval, the transmitted carrier frequency is FC0 plus F1. If you eliminate FC0 part here, then it becomes the D-hopped frequency. So, the D-hopped frequency for the first bit interval is F1. Moving on to the next bit interval, the transmitted carrier frequency is FC4 plus F1. Eliminate the carrier part, what remains is F1. So, it would be the D-hopped frequency for the next bit interval. Extend this theory to the rest of the frequencies and then you will obtain the D-hopped frequencies. I will plot that here by using a very similar approach as what I have done for the part C of the numerical. Let me start with the x-axis here, which represents the time axis. Y-axis represents the frequency axis. However, this is for the D-hopped frequencies. Let me start the operation. Please note, you are writing the plot for the D-hopped frequencies, which are nothing but the MFSK tones. Each MFSK tone here is of length 2 bits. So, when you borrow frequencies from this graph, you have to take frequencies for 2 bits or simply 1 MFSK symbol duration every single time. You cannot take the transmitted frequency for 1 bit, you have to take it compulsorily for 2 bits of information and then eliminate the carrier frequency part. The first 2 bits here are 0, 1, which are a combination for the MFSK tone F1. So, you have to now come back here and write a box across F1 for 2 bits or simply 1 symbol duration. Moving on to the next 2 bits, it is 10 and this stands for MFSK tone F2. So, write another box here for F2. The next 2 bits are 11. 11 stands for MFSK tone F3. So, I will now write a box across F3. Lastly, the last 2 bits are 00. 00 represents MFSK tone F0. So, I will write a box across F0. This is the d-hopped frequencies with respect to time, which is the solution for the part D of the question. Now finally, if you want to know whether the complete operation was correctly done, you simply decode the d-hopped frequencies. If the decoded sequence is equal to the input binary sequence, then the complete operation what you have implemented would be correct. So let me now write the decoded sequence here. The first d-hopped frequency is F1. F1 stands for 0, 1. The next d-hopped frequency is F2. F2 stands for 1, 0. Next we have F3. F3 stands for 1, 1. And lastly we have F0. F0 stands for 0, 0. This is our decoded sequence from the d-hopped frequencies. Now compare this with the input binary sequence, which is also exactly equal to 0, 1, 1, 0, 1, 1, 0, 0. So we can conclude that we have illustrated the fast frequency hopped M-FSK transmission as well as reception successfully. Right, that is the end of this numerical. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.